Hello everybody, welcome to this FAULHABER webinar. Just a few words before starting about FAULHABER. FAULHABER was founded in 1947. The headquarters in Germany, Schöneich, 20 kilometers south of Stuttgart. Now it is third generation, and we have 14 locations worldwide in Europe and in North America for production, development, and research. And with the 30 most important countries covered by our service and sales location, we are covering all the world. We provide drive system solution, motors with several technology, DC, brushless, stepper motor, linear motor, also with integrated electronics. We can provide encoders, so sensor for positioning and for precise speed control. We provide the relative drive electronics. We provide gearheads and linear actuators to complete the whole range of drive system for your application. As you can see, only 30% of our standard product are sold around the world. We have 40% of inquiries for a modified solution, for a special shaft, for a mechanical interface, for cable connectors, and 30% of our business is related to custom solution. This is a drive system designed tailored around your application requirements. My name is Mario Zecchin, and I joined FAULHABER in 2007 as a product manager for motion control. Now I'm taking care about trainings in the digital sales systems. Today we want to show you the thermal behavior of cordless motor. We'll give you a lot of information how to improve the performance of the cordless motors and how to estimate the temperature of winding and housing in a motor. You can place your question in the chat or in the comment section. We will give the answer during this webinar or later by email. So the menu for today is we will talk about power losses, different application. We will talk about the thermal characteristics of cordless motors. We will have a simple way to estimate the motor temperature. We will see some difference. We will talk about the thermal motor protection, motor selection with heating in mind. We will make some selection using the calculations and with the drive calculator tool that we have in our FAULHABER website. Then there will be a possible question and answer during this webinar, will be answered or will be sent by email later. In DC motors, we can start with the best-selling products. DC motor convert electrical power into mechanical rotary power. We give electrical power simply by the motor voltage times the motor current, and the motor deliver mechanical power. This is just to convert revolution per minute in radian per second. So this is simple formula is used to calculate the mechanical power delivered by the motor. This is the speed times the torque. Like every real device, we have friction. Friction are due to the bearing, are due to the commutation system. The brush touching the commutator makes some friction, and this increases the motor current during operation. In DC motor, we can calculate the motor current as a real torque in the application plus the resistance torque. Divided by a coefficient is a torque constant. This means what is the torque produced by the motor for every 1 ampere of current. This is published in the datasheet. Then during operation, the winding heats up due to the Joule effect, and the power losses are simply the motor resistance times the square of the motor current. So we have electrical power delivered by the motor, and the motor deliver mechanical power, but we have power losses due to the friction and due to the Joule effect in the winding. In DC motor, what is rotating is the winding inside the air gap between the housing and the magnet. The magnet is in the stator, is fixed to the stator. There are also other losses. We will have one slide about this related to the PWM control of DC motors, typically when you are using an electronic drive system. When we talk about brushless motor, we have a three-phase system. Power electronics are needed, the drive electronics are needed to drive correctly the brushless motor. And also in this case, the brushless motor deliver mechanical power. The friction in this case, we can reach high speed, we can reach high power because there is no limitation due to the commutation system. The electronic commutation deliver the maximum performance to the motor. We can reach high speed, we can reach high torque. And so in this case, there are two parts of friction. The first one is a constant part, so-called static friction. And then we have a dynamic friction depending on the motor speed. We will see later about this. In brushless motor, the working principle is different in comparison with DC motor. We have the rotor, that is the magnet, while the winding is fixed in the stator. So the magnet is rotating in this case. So for this reason, we have some losses also due to the rotation of the magnet, and the losses are located in the stator. We have some lamination stack to reduce these losses, but we are not able to set it to zero. It's not possible to eliminate all these kind of losses. Losses also occur in the PWM. We will see later about this. And the power losses in this case, in a three-phase system, we have to calculate the RMS value of the current. Square of the RMS current times the motor resistance. This is the Joule effect losses. Also in this case, we deliver electrical power to the motor delivers mechanical power, but we have power losses due to the Joule effect, the friction losses, and the losses in the iron due to the parasitic current, to the eddy current generated by the motion of magnet during rotation to the iron parts of the motor. Here we see some motor operation that typically happens in applications. The first one is the continuous operation where the motor is operating in the maximum efficiency zone. You can see here the efficiency is this green curve here at the no load speed, so without any load applied, the efficiency is zero. The motor does not deliver any torque. And you can see here that we start with the no load speed, so the maximum speed achievable by the motor. And then when the load is increasing, you see that the speed is decreasing and the efficiency value is rising. The maximum value is around 1/10 of the stall torque. Stall torque is when the speed goes down to zero and we have maximum possible torque. So in this region, the battery operated device will have the longest battery lifetime because we are working in the maximum efficiency region. And this is ideal for continuous operation, for example, in application like pump, fans, wheeler robot with a constant speed. And in this case, after a long time, the motor temperature will reach a steady state value. Then we have a second part, is the intermittent operation region, where we have the maximum motor power. In this case, because of the high power, the winding heats up very, very fast. So it's necessary to use an intermittent operation where the motor is operating for a certain time, a certain on time, and the motor is cooling down during the off time. So we have some part like, for example, in industrial automation for robotics, where the motor is moving for a certain amount of time and then it's rest for the rest of the time. So we have some cycle of operation possible. So during on time, the temperature is rising, winding and housing temperature is rising, and during off time, the temperature is going down. In this case, the motor must be cooled down for the best performance. Then we have the impulsive operation region, this region here where we have the maximum torque. In this case, the time where the motor can operate is very limited because of the very fast heat up of the winding. In this case, for a typical application is a lock mechanism where you need a lot of torque for a short amount of time to lock and unlock the mechanism. and the temperature may rise really fast in this case. So you need to, for one-shot operation, operate for a short time and then let the motor cool down. When we consider the region of continuous operation where the efficiency reached the maximum value, then we can have this diagram here. In this diagram for DC motor, you see that we have the dark blue area. This is when the motor is connected to a plastic flange, and the light blue area is when the motor is connected to a metal flange. As you can see, plastic flange has a certain performance area. With metal flange, the motor can dissipate better the heat. So this means that you can get more performance in terms of speed and in terms of torque. For example, with plastic operation here, we have reached 17 millinewton meter maximum. This region here is when the temperature in the winding reached the maximum recommended value. We have 125 degree typically. For certain motor, we reach 155 degree. For very small motor, we reach 85 degrees. So it depends on the type of motors and the motor technology that we have. This region here, you can see that we can reach 26 millinewton meter when the motor is cooled down by a connection with a metallic flame. So the heat can be better dissipated. So we have much more performance. In this dashed line region here, this is suggested for intermittent operation, where you can have a very high torque from the motor, but it's necessary to have a cycle in order to cool down the motor. We will see later the effect of this. So motor on plastic flange, we have a limited performance. Motor on metal flange, we have a much better performance, and intermittent operation, we have the maximum performance, but not in continuous operation. In this diagram, you see the maximum speed is limited in DC motor by the commutation system in order to get a decent length of the lifetime. We can limit this value. If you go over, you can go to 15,000-20,000 RPM, but the lifetime will be reduced. On the other side, you have a limitation by temperature. The temperature in the winding is the most important parameter when we talk about performance of the motor, and the maximum temperature is 125 degrees for this kind of motors, and this is limited by the maximum achievable torque. When we talk about brushless motor, you see that the speed is almost 2 or 3 times, so it's much higher because we don't have anymore the limitation of the commutation system. We have an electronic commutation. So in this case, we also have 3 regions. The first one is when the motor is not cooled, so in air typically. When we connect a plastic flange, we are in this region here, outside the dark blue area. So the light blue area is for when the motor can dissipate thermal energy. In this case is with a plastic flange, and like in this working point here, and then with a metal flange we can reach this value here. So in air we can reach 13.5 millinewton meter. With plastic gear we can reach 15, and with metallic gear we can reach 18.5 millinewton meter of torque. We can go over in intermittent operation with a certain cycle, on time when the motor is operating, off time when the motor is cooling down. You see the black curve here is where you have the thermal limit of the winding, for example, and the thermal limit of the winding in air, so without any dissipation. Also in this case we have a limit by the temperature, in this case here, and a limit by the bearing, typically to get a very long lifetime. The real lifetime limit in brushless motor is the bearing. As a takeaway, the better the power dissipation, the better the motor performance. So it's important to put the motor in a situation where he can easily dissipate the heat generated in the winding. You can see that here there is a parameter, it's a RTH2, reduced by 50% here, reduced by 25% there. This is related to this working point. What does it mean? This means that we have a thermal resistance. This is a thermal resistance against the heat transfer between the winding and the housing, typically, and between the housing and the ambient. So we call RTH1 the thermal resistance between the winding and the housing. And this is typically depending on the motor design. So if we to improve this, we have to redesign completely the motor, for example. And we have the RTH2 between the housing and the ambient. What you can see here, the winding temperature is TW, the housing temperature TH, and TA is the ambient temperature. So depending on the material where we connect mechanically the motor, flange, then we have a different value of thermal resistance. The RTH2 with an external plastic flange, you see there is a 15 Kelvin per watt, and the RTH2 related to the metal flange is 2.1. This means that we have a less resistance against the heat transfer, so the heat can be flowing better to the ambient through the metallic flange in comparison with plastic flange. What happens with the brushless motor? We have a similar situation. There is a thermal resistance between the winding and the housing, and the thermal resistance between the housing and the ambient. TW is indicated as a winding temperature, housing temperature TH, and the ambient temperature TA. So let's see what happens during the operation of a motor in an application. And we have a so-called also thermal time constant. The thermal time constant is the time necessary to reach the 63% of the final temperature. Final temperature that can be 125 degrees for the winding, then the 63% is around 80 degrees. So after this is the time constant necessary to reach this value. After 5 time constant, we can get the maximum value is 99.5. So it's almost 100% of the end temperature. So we can consider after 5 time constant to reach the steady state, the maximum temperature of the motor. As you can see, we have a winding maximum 125 degrees. So we have to take care not to cross this value for a long time, otherwise there could be a damage in the winding. And what you can see is the winding is 12 seconds to reach 80 degrees, for example. The housing connected to a plastic flange, 580 seconds, so the ratio is very, very high. So what we can see that the winding is heating up much faster than the housing. When connected to a metallic flange, we have a better performance, so the dissipation is much better. During heating, the temperature from the ambient temperature to the maximum temperature follow this simple rule. When the time t equals the time constant, then this value is 0.632, something like this. So this means that 63% come from this number. With the same condition, the cooling condition follow the same speed, and this is the formula for the cooling condition. And this is important when we talk about intermittent operation. This is the law where the increase of temperature in the winding, it happens during on time, and when the off time, there is a cool down of the motor with these two rules. So in this case, to calculate the temperature, we have to consider the increase of temperature during on time and during off time. We will see later the effect of this. Remember, the time constant of the winding is much lower than the time constant in the housing. So this means that we don't recommend to use a thermal sensor in order to measure or to estimate the temperature. If you place the sensor in the housing, on the housing, then you measure only the housing temperature, not the winding temperature. We will see the difference later. So how to estimate in an easy way winding and housing temperature? Let's consider a simple DC motor. This DC motor can have a simple thermal model, and this thermal model has a lot of similarity with an electric circuit. In an electric circuit, for example, we have a current, we have resistance, we have a voltage drop across the resistance, we have a total voltage drop like this. Then we can consider the current and the power losses in the thermal model. If we consider the power losses, this is due to the Joule effect. So we have seen the simple formula, resistance times the square of the current. And then we can consider a total temperature variation like a total voltage. And we can consider the thermal resistance like a resistor in an equivalent electrical circuit. So based on this, we can calculate the power losses is a motor resistance times square of the motor current. We can calculate the total variation of temperature between housing plus winding, and this is power losses times the sum of the two thermal resistance. Then we can calculate easily the temperature in the winding point, simply adding the ambient temperature on this point, typically 22 degrees in lab or in normal conditions, plus the variation of the temperature across the housing and the winding. And if we have to calculate the temperature of the housing, we simply add the ambient temperature plus this variation of temperature. So power losses times RTH2. So with this simple model, could be simple to calculate what is the value of temperature reached by winding. Let's see an example. If we use a motor with graphite commutation system, 23 is the diameter, 42 is the motor length. The motor is running 6,000 RPM, and the torque in the application is 18 milliNewton meter. Then we consider the motor mounted on a metallic flange. So what we have to consider in the calculation is the RTH2 value, so this value here, related to the external metal flange. So this is the value that we have to use in the calculation. Based on this, we can calculate the power losses, we can calculate the temperature variation, and we can calculate the winding and the housing temperature with the same formula that we have seen before. Let's see it numerically what happens so we have 6,000 RPM, 18 milliNewton meter, the 2342 motor with a metal flange. So when we have to calculate all the parameters, we start for the motor current calculation. Is the 18 milliNewton meter is the application torque. MR is the friction torque, is this value here. We have to add this value here, friction torque between the brush and the commutator, and added also with the bearing friction. Based on this, the Km is this parameter here, torque constant 28.6. So we reach a value of 0.66 ampere. Based on this, we can calculate the power losses that we use later for calculation of the temperature is 3.11 watts. Based on this, we can calculate the total variation of temperature, that is 24 degrees. Then to calculate the winding temperature, we need to add ambient temperature and the total variation of temperature, we reach 46 degrees with this model. Then the housing is ambient temperature plus power losses times this thermal resistance here. So this means 28.5 degrees. So we can easily check if this is correct with the FAULHABER dry calculator. To get the FAULHABER dry calculator, we have to go with to the FAULHABER website like this. This is our website, and you can start the dry calculator with this link here. Then we can enter simply our data, 6,000 RPM, 18 milliNewton meter. We can select here, click here, you can select the DC motor with graphite commutation. And then below, we can go to select on the global settings. The ambient temperature is 22 degrees. We can restrict the diameter available, 23 millimeters, and then we can have the metal flange. Thank you, Frank, but you cannot have me now. And with a click on calculate, the system calculates all the possible combination that can satisfy this working point. You can see we choose the 2342 with 24 volt. So this is the result page. So what you can see is that load voltage 23 volts, the load current is 682. Let's have a look at what we calculate here. Slightly different, but is not bad. This is a simple model. And then we see the housing temperature is 26, winding temperature 46.8. So it's quite good. We can reach good results here. What can we see? You see here the working point. This working point here is with a 50% reduction of the RTH2. This means that we are connecting the motor with a metallic flange. If we connect the motor to a plastic flange, it will be not possible to use it. Again, this let's have a look at the motor graph. You can see, like we have seen it before, we are in the region of continuous operation. We're in the region where the efficiency reached the maximum value. In this case, you see also the value of speed, 6,000 RPM, the 18 milliNewton meter of torque. One thing that I want to show you here is in our model that winding temperature is 46 and the housing temperature is 20 degrees lower. This means that if you place a thermal sensor to measure the motor temperature, you measure only the housing temperature, but you have 20 degrees more on the winding. So take care about this. Don't consider the temperature sensor as an absolute value also for the winding. What happens here when we increase the torque? Let's ask for more torque in the motor. So instead of 6,018 milliNewton meter, we go to 30 milliNewton meter. So this could be, for example, in continuous operation when you have a belt system for transportation and you have a heavy weight instead of a lighter weight as before. So 30 milliNewton meter on metal flange. What happens here in this case? So we reach 1.08, the new value of current. This leads to a 8.3 watts of power losses, and the temperature is changing. The total variation of temperature is 64 degrees in this case. This brings the winding at 86 degrees and the housing at 40 degrees. So we have an increase of temperature, of course, like this is logic. We have more current, we have more power, and then the temperature is rising. 86 degrees. What happens in the drive calculator? When from this page here, we can go down, scrolling down, we can modify the input value, and then we can select 30 milliNewton meter under the same conditions. Let's calculate and let's see what happens with the same motor. Now you can see that the results, we have 86, but now the calculated value is 170. That's a problem. Why we have this huge difference in this case? So the drive calculator give a much higher value. You can see 1.2 ampere of current. We are on the limit of intermittent operation. And if we look here, another thing is the temperature, 36 of the 0.7 in the housing and 100. Almost 120 on the winding. So there is a huge difference of temperature between housing and the winding. And if you see that this diagram here, we are working now near the region of maximum power. This means that we need to operate in intermittent operation and not anymore in continuous operation. So we can also have a look what happens to the motor in this condition. We go back to the input page, and with the same value, instead of continuous operation, let's consider intermittent operation. What happens in this case? we have this value. This could be possible for a certain amount of seconds. Let's put 10 seconds, and let's consider 2 seconds of time off, or even more, 3 seconds. We can play with this. The number of cycles is important because during on time the temperature is rising, during off time is falling down. We need a lot of cycles in order to reach the final temperature. Let's consider, for example, 500 cycles. In this case, we can click on the calculate button, and the system gives us all the possible motors that can satisfy. You can see that we have a list of much more motors than before, because in intermittent operation we can reach a lower value. Let's stay with the 2342, and let's consider what happens here. In intermittent operation, you see the winding temperature from 170 drops down to 87. So in this case, we need a little bit more. Let's say instead of 500 cycles, maybe we need 1000 cycles to reach the maximum temperature. This could be around 90 degrees, more or less. This blue line is the temperature in the housing, and the red one is in the winding. So the maximum value when the motor is heating up, and the minimum value is when the motor is going down. So you have an up and down cycle like this, and this is because we have 500 cycles. So you see this this curve here in reality is an up and down curve like this. So why this large difference that we have seen before when we had, for example, the continuous operation? We had 117 degrees instead of the value of 86. This is because this simple model is valid up to 60 degrees, more or less. The effect of the temperature is really important in this case. We have two main effects in this case. The winding resistance is increasing because of the copper coefficient is 0.0039 on Kelvin. This is the variation for each degree Celsius. And you can see that with this formula here, when we have a delta T, a difference of temperature of 100 degrees, we can have 40% of variation in the motor resistance. So this is a huge variation, and this causes some effect. With the same supply voltage, with 100 degree value, then we have a higher resistance. This means lower current. So we have a lower torque. The second effect is on the magnet. We use neodymium. Neodymium is a very, very strong material for the magnets, but we have some temperature coefficient, and in minus 0.1, this means that with the increment of temperature, the performance of the magnet is reduced. We have a loss of around 10% when the temperature is rising 100 degrees. So the Km depends on the motor magnets, so that Km fall down when the temperature increases. So we have a double effect because of this. The motor gets weaker when the winding and the magnet increase the temperature. It's necessary to have a recursive calculation, so we have to recalculate the new motor resistance at the new value, for example, 117 degrees, and then we have to calculate the winding temperature. We have to calculate the new Km at 117 degrees, for example, and we have to calculate the new temperature. Then with this, after 2 or 3 iterations, we can reach the final value. Remember, it's not necessary to know exactly the motor temperature at the decimal point. It's important to understand if this motor can withstand the application requirements or not, so can satisfy the application requirement or not. So once we have a calculation of the new RMOT and the new Km, then we can calculate the new value of the winding and housing temperature, just for an estimation around this. What happens with brushless motor? We have the friction torque. We have seen it before. We have a constant part, the static. The second one is the dynamic friction, depending on the motor speed. For high speed, this component is much important than the constant static friction torque. This is the value. We can use this value here. The resistant torque is the sum of the two frictions depending on the speed, and when we talk about the motor current, we have this value here divided by the km. Application torque plus the resistant torque in brushless motor with the two components. One is fixed and the second one depends on the motor speed. So with the simplified model, in this case, there could be a larger difference. We have to introduce some other parts related to the losses in this case, but with the drive calculation tool that in our website, you can see in a few clicks, you can get the precise results, you can get the precise value of winding and the housing temperature in a few seconds. Let's see some operation mode and what happens to the motor parts. The temperature when you start the motor in continuous operation, for example, the winding temperature is rising. The housing temperature is rising much slower. We have seen it before because of the different time constants. And the magnet is heating up by the winding. Typically, he cannot dissipate a lot of heat, and we can reach almost the same temperature of the winding after a long time in continuous operation. What happens to the motor current? If we use a motor current below the nominal value, so below the current that allowed the winding to reach 125 degrees, for example, we have no problem at all. When the motor reaches the nominal value, then we can go near the limits. And if we use a higher current, then we can easily exceed the critical value in this case. But in this case, we need to operate in intermittent operation. So in intermittent operation, you see better here, the motor temperature is rising and falling down, rising in on time, falling down in off time. And you can see this is a typical trend until we get the stable value after a certain amount of cycles. For example, here is after 8,000 cycles. Then you can see that magnet temperature is lower than the maximum value for the winding. We have not to exceed the 125 value here with the maximum value. And you can see the movement of temperature, the variation of temperature for the housing is much lower than the winding temperature. So in this case, the winding temperature is always over the housing temperature. And in this case, we have to calculate the RMS current instead of the continuous current and consider this to calculate the value of the winding temperature to be below the recommended temperature value. What happens with the PWM? We have seen that PWM also causes losses, and now in drive electronics is a standard to use PWM control. This is a supply with a very fast frequency, where fast the control electronic open and close very fast the switch. When the switch is closed, the motor sees the voltage, and when the switch is open, the motor sees 0. So you can see here the maximum voltage here, and open you see 0 voltage. And this, depending on the so-called duty cycle, the duty cycle is the ratio between the on time when the motor receives the maximum voltage and the total length of the cycle. This is a fast movement. We have a very high frequency in this case, in the magnitude of more than 20 kilohertz, for example. And if the duty cycle is 75%, this means that the T on time is 75% of the total cycle time. In this case, the motor voltage is 18 volts, is 75% of the applied voltage. So when we switch on and off the motor in a fast way, the motor current is rising fast and on time and is going down in off time. And you can see that we have a huge current variation. And this is especially for a coreless motor where we don't have any iron core, so the inductance of the motor is very low. In this case, the variation of the current is very important. We have a large ripple, and the worst case in this case when the duty cycle is between 40 and 60%. In this case, the effect of the current ripple is the maximum. The electrical time constant affects the rise and the fall time of the, so also the ripple of current in the coreless motors. And then let's have a look at what happens to the critical part of the motor when we have this high current ripple, high current variation. Let's consider 24 kilohertz of PWM frequency. With a coreless motor, you can see that we have a very fast current rise and very fast current decrement. And then what we see is that we can have a problem on the commutator side, because we have a lot of difference in between the average current, this value here, and the RMS current. This difference causes heat generation. Heat generation means that we may have a shortened lifetime of the commutation system. A possible improvement in this is to add power inductance in series with the motor leads, like in this case here. In this case, we have an increment of the total inductance. Like this, you can see that we have the possibility to, with more inductance, we have a less current variation, less heat generation, but at the same time, we also have a slower current response, so less dynamics in the motor. For this, we have an application notes. I show you where you can find it in our FAULHABER website. When you go to the homepage, and then you can find the know-how section, where you can find a lot of information, tutorial, application notes. In this section, you can find a lot of information related to our motors. Let's choose for the application notes related to the PWM and to the additional inductance. Is this one, reduction of PWM. If you download this, and then you can open it with a PDF reader, and here you can find a lot of interesting information related to the effect of the additional inductance, which kind of motor you can use, what happens to the motor operating area, and so on. You can see here the losses are between 40 and 60%. We have maximum losses. There is a lot of interesting information how to use the external inductance in combination with our motors. A possible improvement is increasing the PWM frequency. Using high PWM frequency, you can see that the current ripple is much more reduced. This means that the difference between average and RMS current is smaller, and we have a less heat generation to get the same dynamics from the motor. In this case, for example, our speed controller series have 96 kilohertz, and our motion control systems, motion controllers use 100 kilohertz, but this is the particular configuration of the PWM generator. We reach visually 200 kilohertz on the motor. So very high PWM frequency means very low current variation, current ripple, so less heat generation. Let's talk about the thermal motor protection. This means that we can measure the power flow through the motor, and this power flow is measured proportional to the I square T, so the motor current square times the time necessary to operate the motor. In this case, for example, the energy is the power times the time power is I squared times Rm. This is why we talk about I squared T algorithm. So the motor resistance times the time times the square of the current. During normal operation, we have seen it before, when the current is much higher for a long time, we have a damage in the winding. With the thermal limits, it's okay. When we have the motor current at the nominal value, we limit at the thermal limit the winding temperature. Never problem with the normal operation when the current is lower than the nominal voltage, nominal temperature, sorry. So below the thermal limits, we can overload the motor for a certain time. It's important to reduce the thermal resistance between the housing and the ambient. So forced air blowing or with a larger dissipator, we can get much better performance, and we can reduce also the winding temperature, as we have seen before in the calculation. And the peak current must be limited at a certain time, otherwise we damage the current. Typically, a rule of thumb is when the peak current is higher, then we have to reduce the permissible time allowable for this increase of current. Also, is very important the ambient temperature. Instead of operating to 22 degrees, when we operated to, for example, 50 degrees, then everything is shifted up, so the temperature in the winding and in the housing will be increased. In our drive electronics, we use this algorithm. We have a situation like this. We have a model value for, let's say, a mathematical model implemented in our firmware to estimate the winding temperature and the housing temperature. When the winding temperature reach a critical value because of the increase of load, we reach a peak current, and then after, when the model calculates that the temperature is crossing the maximum value, 125 degrees typically, then the motor current is reduced to the continuous value. In this case, the maximum temperature is limited on the motor, and we save the winding. Then after that, you can see 4 points, and you see here we have a larger current for a longer time, because the I squared T algorithm calculates when the motor reached the critical temperature. So this is not a fixed value. This depends on the energy dissipated from the motor. So again, in the FAULHABER speed controller series, we have a peak current that is twice the nominal current, and in motion controller, the motion control system, we have 3 times this value. During operation, the winding temperature must be frequently calculated in order to be sure that we don't have high current, so high dissipation for a long time, to save the winding from overheating. So we are reached the end of this webinar. To recap everything, we have seen that the temperature is a key factor in drive system. We need to keep the winding temperature below the critical value. Thermal resistance and thermal time constant, we have seen it. This is important parameter for the estimation of the winding and the housing temperature. We have seen the importance to reduce the RTH2 between the housing and the ambient. With a metallic flange, we can reach higher performance in comparison with plastic flange or no isolated motor. We have seen that with low PWM frequency, we have a large current variation. We may have a shortened lifetime, especially for DC motors. And with high frequency, we can limit the motor overheating to get the same performance. In intermittent operation, the on time of the motor is important. So we have to calculate the cycle in order not to get over the critical temperature, and limitation of the motor current is a good strategy to avoid the motor overheating. So we have reached the end of this webinar. The know-how section, you can have here the information where you can find out information, where you can find out our know-how section. You can see our webinars, you can see the drive calculator that we have used in this webinar. You can see the drive time video, the short video that explain how to work in the best way as possible with our motor. Is a 5-minute video. You can find it in our website and in YouTube. And then we have the application notes and the tutorial where you can find a lot of information. So I thank you for your attention and see you soon.